Okay. Okay, so Shubho Vijaya to all of you. Though a bit late after a long time for meeting. And Shayan probably has taken morning class today, right? What did he teach? Huh? Huh? Electrodynamics has just started. He is doing free field theory so far. Today he did scalar QED. Means scalar field coupled to electromagnetic field. Okay. Anyway, so far what he has done is basically he has dealt with so-called bosonic field theory. Both scalar field theory and Maxwell field theory, the quantas, if you see them, they satisfy so-called commutation relations. And also the field theory we are doing here, and we will be doing actually all throughout, even if some people opt for quantum field theory in the second semester, it will basically confine to what is called zero temperature quantum field theory. Finite temperature field theory is beyond your syllabus. Field theory is a very huge subject. Okay, very, very huge, and is the deepest area of theoretical physics. Okay, so what I intend to do to start by discussing the Dirac equation, because that has not been covered, as I have been come to know. That should have been covered in second semester quantum mechanics course itself, relativistic quantum mechanics, but it was not. Huh? Kore dao. Okay. So is it audible now? Okay. So what happens is that Dirac equation I have already taught you actually in group theory class, if you remember. It comes from SL to C transformation. So I did not do everything, but I will just give a short pedagogy of what has been, means how Dirac did it historically. Just get a flavor of the historical development of this Dirac equation, celebrated Dirac equation. Okay. So Shayan probably told you that. না স্কেলার ফিল্ডে দেখানো হয়েছে তো যে এটার অ্যাঙ্গুলার কোয়ান্টাম অ্যাঙ্গুলার মোমেন্টাম গুলো জিরো হয়, ইন্ট্রিনসিক অ্যাঙ্গুলার মোমেন্টাম, এটা দেখানো হয়নি না? হ্যাঁ, ওকে, I'll do it. That should have been done anyway. So so what I'll do Dirac equation. So let me do towards Dirac equation. Historically, as you mean, I did not elaborate because we have already been doing Klein-Gordon field theory. Historically, you see, means I'll be working in the unit of h bar and c is equal to 1. Okay, for convenience. So historically, you see, means this Einstein's dispersion relation E square is equal to p square plus m square. This is the dispersion relation. And once this is Einstein's dispersion relation. That's what you have learned in special relativity. Okay. So after the great success of non-relativistic quantum mechanics, Schrodinger himself worried.
স্যার স্যার লেখাগুলো মানে খুবই ছোট দেখাচ্ছে, ঠিক মানে
Oh, okay. I'll try to write. But this is Einstein's dispersion relation. E
হ্যাঁ স্যার
square is equal to b. Now, up to this is all right. Henceforth, I will write everything in big fonts.
ওকে স্যার
Okay. So, this dispersion relation is relativistic, unlike E is equal to p square by 2m. I am talking about just free particle. Okay. So, you know that non-relativistic dispersion relation gave rise to Schrodinger equation roughly. You replace E by I del del t and P by minus I del del x kind of thing. And then you substitute in the E is equal to P square by 2m. Then if you add potential, if you are dealing with particle moving in a potential, and you end up with Schrodinger equation, right? But Schrodinger equation has the disadvantage or advantage, whatever you say, that it is different in time and space, because time derivative occurs the first derivative and special derivatives are second order derivatives. So there is a mismatch. This is not a big deal because you are in a non-relativistic regime, so you can say that okay, it is not mandated to treat space and time on the equal footing as far as transformation property is concerned. But you can anticipate that you will run into difficulty the moment you are discussing relativistic phenomena where space and time are equal footing and you have to invoke special theoretical relativity of Einstein. So, if time is linear, first order in time derivative, the energy part, Hamiltonian part, so the momentum part will also be first order derivative. Or else if it is second order derivative, that also should be second order. Well, that means there should be parity between time and space. Okay. Whatever order you have for the special derivative, the same order should be there for the temporal derivative, time derivative also. This is the basic idea. So the Klein-Gordon equation when you write, then you just replace these things, you get box minus m square phi equal to 0, phi that you have already Cheyenne probably wrote for you, right? So box means the D'Alembert del mu. If you write del t square minus del Laplacian square. Okay. From here, you can say that okay, I deal with what is called not real field, scalar field, but the complex scalar field, and the Noether's theorem tells you how to obtain the conserved current. So the conserved current in the 4-component notation is something like this. 2 mi, I think. Okay, phi star del mu phi, something like this. This double arrow this way, that way means first term is derivative acting on phi minus another term where the derivative acts on phi star. Okay. So this is the notation. A B is equal to A del mu B minus del mu AB. Okay. This is the notation I am using quite frequently. It's a relative minus sign, you should keep in mind. Okay. So you have this factor, I am writing from memory, it may be correcting mismatches there. You don't bother. The point I want to emphasize is that J mu has this form. So it satisfies the continuity equation del mu J mu is equal to 0. This is a continuity equation.
স্যার
Yes.
স্যার বলছি ওটা j mu equal to 1 by কি লিখেছেন?
1 by 2 mi. Means that's prefactor, I'm not 100% sure. I can derive it, but I'm not doing because Cheyenne has probably done all these things for you. Okay.
ও আচ্ছা হুম। স্যার বলছি
Just
যে এই মানে ক্যামেরার যে ইয়েটা আছে একটু যদি ঠিক রকম করা যেত ভালো হতো, মানে ঠিক দেখতে পাচ্ছি না আর কি।
কিন্তু এখানে তো ক্যামেরায় ভালোই আসছে দেখছি আমি, মানে ডেস্কটপে।
মানে স্যার আপনি বড় করে লেখার পরেও একটু ছোট ছোট মনে হচ্ছে।
পারবে ঠিক করতে? শোনো, আচ্ছা এই ফ্যানটা একটু খালি চালিয়ে দিতে পারবে? আচ্ছা দেখো,
সৌমিক আর একটু কাছে নিয়ে যাবো বোর্ডটা। হ্যাঁ হ্যাঁ ঠিক ঠিক আছে, হ্যাঁ বেটার, হ্যাঁ বেটার।
okay, so this is the continuity equation, and the moment you arrive at continuity equation, you know the J0 will be something like phi star del naught phi minus del naught phi star phi. That will be your J naught, right? But presence of minus sign tells you that you cannot have actually a positive definite condition for J naught. So this Klein-Gordon equation, this is a Klein-Gordon equation was discarded in the first stage when you try to do relativistic quantum mechanics with Klein-Gordon equation. Okay, it was resurrected later, so to say, when you do second quantization and you have done field theory using the second quantization method, right? So there you see that this kind of difficulty are completely evaded. But here I am talking about the first quantization, the quantum mechanics itself. Okay. So here it was discarded that you cannot proceed even to the basic level because you cannot give a viable probabilistic interpretation to this so-called wave function phi. Okay, it is not positive definite. So this interpretation, which was very successful in non-relativistic case, was not so here, so you discard it. Then came Dirac in the picture. He immediately realized that although the parity between space and time has been restored here, unlike in the Schrodinger equation, because both are second order in time, both involve second order derivatives, but the very presence of the second order derivatives implies that this kind of system are beset with another problem, which is that if you consider energy, just you take square root of both sides, you get plus minus p square plus m square, square root of p square plus m square, and plus minus sign indicates that you have a negative energy states also in the system. So there is no lower bound. You cannot do quantum mechanics with this. Okay. So he anticipated that the problem probably can be sorted out if we can write down some sort of equation where space and time derivatives will be first order, only first order, no higher order, no second order. Okay, first order in space and time. So how to do that? For that, he observed, let me erase this thing. he observed that here you have the D'Alembert. So I need some sort of a square root of the D'Alembert operator. But D'Alembert operator involves del t square minus Laplacian. So he says that, okay, let me first try to find a square root of the Laplacian itself, whether I can find, and then it will be easiest in 2 dimensions. In 1 dimension is trivial. Square root of del square del x square root is del x. It means square root of an operator, I mean, if you, the square root will be such that when you square it, you get back the original thing. Okay. So he tried, initially you have to do simpler exercises and then you do the more general case. So he started playing with the usual Laplacian in 2-dimensional plane. How does it look like? This looks like del x square plus del y square, right? Del x, I am writing shorthand notation. I hope you are familiar because you have done general relativity. So there is no problem. Del x is del x, del y is del y. So this is the Laplacian and these things. Question is, can we find a square root of these things? Square root means a linear order in del x. Okay. This is the simplest example. 1 dimension is trivial. That you know, del x square means it will be just del x. So 2 dimension will bring in some non-triviality. Okay. So you postulate something like this. I call it D. Write it, let me write it some alpha x del x plus alpha y del y. I don't know what alpha x and alpha y are. I just have no idea. So I demand this is the first order in the derivatives. Here I am considering all the coordinates to be spatial, not temporal. The presence of time will bring in another complication in the respect of minus sign, the relative minus sign. So that's why I am telling you, first do the simplest case and then slowly develop or generalize to the more complicated case. Okay. So I want to find what are these quantities, alpha x, alpha y. Does there exist any quantities, alpha x, alpha y, such that upon squaring this object, I get this. And this kind of, so this should satisfy this d square is equal to Laplacian. Okay. So I take d square will be alpha x square del x square plus alpha y square del y square plus alpha x alpha y delta x delta y plus alpha y alpha x delta y delta x. Laplacian means this operator, which is linear, upon squaring it, it should give me the Laplacian. This is the definition. I am looking for an operator which involves only linear order derivatives of the variables x and y here, so that if you square it, you get hold of the Laplacian. Okay. So now del x del y, they are being ordinary derivative, they really commute. But the order doesn't matter. So I can club these things as alpha x, alpha y plus alpha y, alpha x, delta x, delta y. You see, I am not disturbing the order of this alpha x, alpha y because I don't know what kind of objects they are. There may not be simple numbers. There can be matrices. So I'm keeping the door open. Okay. So I'm not, but I know that these partial derivatives, they commute. That's why I'm clubbing them together. Okay. So now this should be equal to delta x square by demand. Delta x square plus delta y square. So if you compare, what do you get? You get alpha x square is equal to alpha y square is equal to 1. Coefficient of this thing is 1 here. Delta y square coefficient is also 1 here. And this thing should add up to 0. Is that it? So alpha x, alpha y plus alpha y, alpha x should add up to 0. So you have to find, so now the task is reduced to finding these quantities alpha x and alpha y such that these two pair of conditions are fulfilled. Okay. Clearly, there doesn't exist any number which does this job. Okay. No real number or complex number will do this job. Any complex number you take, you add them. If you find it to be 0, then those numbers themselves have to be 0. And those numbers cannot, upon squaring, can give you 1. Okay, you can try with any complex number. You will find no solution. If you dealt with number, then this alpha x, alpha y has to be restricted to plus or minus 1. Right? So you will not be able to find this. So what are the solutions? Solutions you have learned in non-realistic quantum mechanics, they are the Pauli matrices. Choose alpha x equal to sigma 1 and alpha y to be sigma 2. You know that sigma 1 square is 1, sigma 2 square is 1, and sigma 1 sigma 2 plus sigma 2 sigma 1 is 0. Right? If you remember, sigma 1 was 0, 1, 1, 0. And sigma 2 was 0 minus I 0. Okay. There is another Pauli matrix which I will use later. It's called sigma 3, which is 1, 0, 0, minus 1. Okay. So this is this such kind of operator. So what I have ultimately, I have the operator D, which is sigma 1. Instead of del x, I write del 1 plus sigma 2 del 2. Instead of x, I am writing 1. Instead of y, I am writing 2. This is the convention used even in general relativity, right? So such kind of operator, which upon squaring gives you the Laplacian, is called Dirac operator. Okay. It's okay. Now, so Dirac operator for R2, I am considering this was my Laplacian for a plane which I denote by R2. Okay, this was my Laplacian, and this is the corresponding Dirac operator. Corresponding Dirac operator. Okay, you could go ahead and ask what will be the I know the Laplacian for R3. Huh? What will be the Dirac operator for these things? You can easily guess. So let me erase these things. I hope I can erase everything. So Dirac operator for R3. So you start with the Laplacian here. And is del 1 square plus del 2 square plus del 3 square. 1 means x, 2 means y, 3 means z. So del x square plus del y square plus del z square. You can easily guess what will be the Dirac operator. The Dirac operator will be d is equal to sigma 1 del 1 plus sigma 2 del 2 plus sigma 3 del 3. We'll take their square to show that this indeed is satisfied. Okay. You can write it more compactly as these things sigma I del I, where summation equal to 1, 2, 3. I is a repeated index, it is being summed, and range is 1 to 3. So you take d square, you have sigma I del I, sigma j del j, another dummy index you have to write, isn't it? Sigma I del I, and sigma and del, these are partial derivatives, they act on some functions. And these are matrices sigma. So you can interchange this partial derivative and these matrices. Okay. I hope it is clear. If you don't follow, you ask me. So now you know you are an expert in tensor analysis. You have done it in curved spaces. So this is a simple flat space expression. So you symmetrize and anti-symmetrize. So you have sigma I, sigma j plus sigma I, sigma j. So you have, this is called anti-commutator. You have seen this thing, anti-commutator, right? A commutator, anti-commutator will be, this is the notation. AB is equal to AB plus BA. And these things, A comma B is equal to AB minus BA. Okay. So, this is symmetrization. This is the definition, no? Instead, or del I del j, yeah, that I have for del I del j. They commute, so I don't have to bother about these things. So now, what is these things? You know, this Pauli matrices satisfy anti-commutation relation. This is twice delta ij identity matrix. Don't you know Pauli matrices property? This is delta ij, and this is what? This is 2I epsilon I j k sigma k. Isn't it? So what do you get? This term is anti-symmetric on INJ, and this is symmetric. So whenever you have terms where there are indices where indices which are being contracted, in one case they are symmetric, another case is anti-symmetric, they collapse to 0. You know this, right? So this term will not contribute. This will give you 0. And this will give you twice delta ij. This 2 will cancel with this 2. Delta ij will make it del I, which is nothing but Laplacian. So you have verified Dirac operator square indeed gives you the Laplacian. So the claim is that Dirac operator for R3 is this: sigma I del I equal to 1, 2, 3. Two dimension also it was sigma I del I, but I was running from 1 to 2. That way you can generalize it to higher order, but sigmas will not be sufficient. I am coming to that. Because then you have to find higher dimensional matrices. Okay. But the thing is, huh? Oh, this is epsilon ijk, commutation relation, 2i epsilon. This is antisymmetric in their ij, and this is symmetric under ij. Antisymmetric and symmetric tensors, when they contract, give you 0. That you know the reason also, I hope. Huh? Okay. Huh? 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 মানে আসছি আমরা আস্তে আস্তে করে আসছি, কিন্তু ডায়াগনোজ করলো, ধরো ডাক্তার ওষুধ করলো, ডায়াগনোজ করে, ও ডায়াগনোজ করলো যে ফার্স্ট অর্ডার সেকেন্ড অর্ডার টাইম ডেরিভেটিভ আছে বলেই প্রবলেম, ফার্স্ট অর্ডার করলো, ফার্স্ট অর্ডার করতে গিয়ে এত সব করতে হলো, কুস্তি করে এটাকে নিয়ে এলো এই ফর্মে, বললো এটা তো হ্যাঁ হ্যাঁ লিনিয়ার টাইম ডেরিভেটিভ লিনিয়ার, স্পেশাল ডেরিভেটিভ লিনিয়ার থাকবে। এখানে অবশ্য আমি ইউক্লিডিয়ান স্পেসে করছি, আমি পরে আসছি স্পেস টাইমে, কিন্তু আমি কি করে জেনারেল ডিরাক অপারেটর কনস্ট্রাক্ট করবো এই ফর্মালিজমটা বলছি। ইজ ইট ক্লিয়ার? ওটা আসছি, আই এম কামিং টু দ্যাট। ইনফ্যাক্ট দিস ইজ দ্য প্রবলেম আই ওয়ান্ট টু ডু 3 + 1 dimension. I've done 3 dimension, I'll do 4 dimension. 4 dimension, but with another complication, that is a relative minus sign for time. D'Alembert is del t square minus del x square minus del y square minus del z square, right? The relative sign of minus sign is there. So we'll do it. So, but before we go for 3 + 1 dimension, we want to make sure that you observe certain features. In 2 dimension, you had, so let me again erase it. So, Dirac operator for 2 dimension and 3 dimension. Let me call it D2 is sigma 1 del 1 plus sigma 2 del 2. And 3 dimension, it was sigma 1 del 1 plus sigma 2 del 2 plus sigma 3 del 3. Okay. Even dimension and odd dimensions, they are a bit different in nature. Why? The reason is that the product of sigma 1 and sigma 2 gives you sigma 3. Do you remember? You take these matrices and take their product, sigma 1, sigma 2 is equal to I sigma 3. Okay. So up to a factor of I, it gives you sigma 3. So the moment you are in 2 dimension, you take all these coefficients which are Pauli matrices and take their product, they'll give you the coefficient which is required to be inserted when you construct Dirac operator for next higher odd dimensional space. Okay. So, in fact, this is a feature which is going to persist for all general this thing. So, even in, if you consider the These are called Dirac matrices in more general context. In two dimensions, these are Pauli matrices, but in general, they are called Dirac matrices. What I am saying is that these matrices which occurs as coefficients, you see there is a freedom. You could have, instead of sigma 1, sigma 2, you could have chosen sigma 2, sigma 3. You could have chosen sigma 2, sigma 3 because all of them satisfy the same kind of algebra. You have the freedom, but you have to choose two of them. I have chosen as per convention these two. What I observed is that if I go to the next higher dimension, which is odd, I've started with the even dimensional Dirac operator, and when I go to the next higher dimension, which is odd, the next coefficient will be obtained by taking product of these two. Because sigma 1, sigma 2 is up to a factor of I is sigma 3. You may think that, okay, can't I go to the next fourth dimension by taking their product? No, it will not work. If you take product of sigma 1, sigma 2, sigma 3, it will give you identity. Proportional to sigma 1, sigma 2 is sigma I sigma 3. Another product of sigma 3 will give I sigma 3 square. So it will become just I. It will not work. Fourth thing. So from even to odd you can go, but odd to even you cannot go. This is a lesson you learned right from the very beginning. Okay. So, and this feature will persist for any arbitrary event 2n to 2n plus 1. Okay. So, now let me go to, so what happens is that you cannot work with the sigmas anymore. Sigmas will not be the viable candidate. Okay. So what do? When you go to fourth dimension, you can do the same exercise in the Euclidean fourth dimension. But I'll do the Minkowski in fourth dimension because I don't have time to do. I'll leave this as an exercise, please note down. Show me. Work out the Dirac operator for R4. This Euclidean R4. Okay? Well, Laplacian is del x square plus del y square, or let me write 1, 2, del 2 square plus del 3 square plus del 4 square. What is D? This is a homework. Okay. You just find out. You see that sigmas will not suffice. Okay. So let me do the problem I will be interested in the case of R1, 3. 1 means 1 time 3 space, total 4 dimension like this. The signature is different. This is the Minkowski thing. That's what I am interested from physics point of view. Okay. Any question at this stage? Okay.
স্যার হোমওয়ার্কটা একবার বলবেন
Huh?
হোমওয়ার্কের কোশ্চেনটা একবার বলবেন
The question is, I have done D2, D3, and I have shown from as you go from this even to odd dimension, the simple technique is you find the matrices by just taking their product. That will give you sigma 3. But from odd to next even, you cannot do it. You run out of these matrices. Because if you take all the products of sigma 1, sigma 2, sigma 3, this will give you just a number. You will not get another matrix. Okay. So going from 3 dimension to 4 dimension is bit non-trivial. You have to find, you will see that you have need a 4 by 4 matrices. Here 2 by 2 matrices was good enough. There you will find that you need a 4 dimensional matrices. So Dirac matrices in 4 dimension, be it Euclidean or Lorentzian or Minkowskian, whatever you say, are not the original Pauli matrices anymore, but they are actually Pauli matrices actually are building blocks of those matrices. You can show that Means I have in group theory class I have shown you how to take a direct product of matrices, tensor product of matrices, right? So they can be written in terms of tensor product of Pauli matrices. So they are the building. So the Pauli matrices are the building blocks, so to say. But that I'll come later. Okay. For the time being, how do you? Yes. Any question? Huh? হ্যাঁ কাজ হয়ে যাবে হ্যাঁ অর থেকে অরে ইভেন exactly you have got the right, you have articulated rightly. Okay, so let me do R1, 3. So here, instead of the Laplacian, I have the D'Alembertian, which I write X box del 0 square minus del 1 square minus del 2 square minus del 3 square. I'm using the signature convention 1 minus 1 minus 1 minus 1. Okay, this called 1 plus minus minus minus. Or for simplicity, they are referred to as mostly negative signature. The other opposite is minus plus plus plus. This is mostly positive signature. So I'm using the mostly negative signature. Okay. You have seen many books, they adopt different conventions, but you should be able to translate one from the other. There should not be a big problem. Okay. So in my class also, I will not be sticking to one convention only. So sometimes I'll pick up some other convention, and onus lies with you to translate it from one convention to the other. It is not a difficult job. Okay. So what is the Dirac operator? So again, I take this thing and such Dirac operator is linear combination of the derivative operator, gamma mu del mu. Now you see I'm doing things in the Lorentzian space-time, so upper index and lower index have to be dealt separately and cautiously. In Euclidean signature, when you deal with, you need not bother, you can recklessly manipulate the indices. I don't have, because raising or lowering cost you no sign. Okay. But in this case, you have to be very, very careful. Okay. Because of the signature convention, the moment you raise or lower a special index, it will cost you a minus sign. Time index will cost you no sign. So you should be very careful about it. Okay. So this is my L such. So demand that d square is equal to gamma mu del mu, gamma nu del nu. I have just written the, because I can now anticipate there will be matrices and constant matrices. Okay, this should be your eta mu nu del mu del mu. That is your eta mu nu del mu del mu. Okay. Because if you just expand it, you will get this. Eta 0 0, eta is plus 1, eta 0 0 is plus 1, eta 1 1 is minus 1, eta 2 2 is minus 1, eta 3 3 is minus 1, and off diagonal elements all are 0. If you just expand it, you will get this. So in short, I can write it like this. I hope you are clear about it. Okay. So this should be satisfied. Again, invoking the same trick, I can symmetrize or anti-symmetrize. Gamma nu, if I anti-symmetrize, this is symmetrized, so it will collapse. So the only symmetrized part will survive. Okay. So I can write down this as half gamma nu plus gamma mu, which is nothing but this notation. Is it clear? Huh? Del mu. You see, we should be very careful when you are doing tensor manipulation. As it stands, this eta mu nu is symmetric under interchange of mu nu. Okay. As it stands here, gamma nu is not symmetric. So you cannot just blindly put gamma mu equal to eta mu nu. That will be wrong. Because this is symmetric and this is non-symmetric. So to ensure that both of them enjoy the same symmetry property, so you have to symmetrize it and write it like this. There is another term, antisymmetric part, but which will upon contraction in del nu will not survive. Okay. So I can just retain this term. Now it is by very construction, it is symmetric under interchange of mu nu like this. So I can equate this with this. So I get gamma nu is equal to twice eta mu nu. This is some identity matrix. These are not numbers, these are matrix, so should have some number. তুমি একটু মুখটা খুলে বলো, কিছু বোঝা যাচ্ছে না। হ্যাঁ, হ্যাঁ, মানে এটা ইনফ্যাক্ট আমি এটা ইউজ না করলেও পারতাম। আমি তো সিমেট্রিক অ্যান্টিসিমেট্রিক জাস্ট সিগমা সিগমাটি অ্যান্টি কমিউটেটর লিখতাম, লিখে বলতাম দেখো এটা অ্যান্টিসিমেট্রিক আছে, ওটা অটোমেটিকলি কোলাপস করে যাচ্ছে। গামা আমি বের করিনি এখনো, আমি বুঝতে পারছি এটা ম্যাট্রিক্স ভ্যালুড হবে আমার আগের এক্সপিরিয়েন্স থেকে, অভিজ্ঞতা থেকে। বুঝতে পারছো? আমি আগের অভিজ্ঞতা থেকে বুঝতে পারছি এটা দেয়ার শুড বি সাম ম্যাট্রিক্স ভ্যালুড। এবং কি ম্যাট্রিক্স হবে সেটা আমি এখন বের করব এই কন্ডিশন থেকে। দিস ইজ মাই কন্ডিশন। I'll give you, there are infinitely many solutions of gammas. ওখানে যেমন sigmas, you take any sigma which is related by some unitary transformation, that will also give you a valid this thing. This is not a unique choice. তোমাদের বললামই, ধরো sigma 1 sigma 2 নিতে পারো, sigma 2 sigma 3 নিতে পারো, sigma 3 sigma 1 নিতে পারো, or any some s sigma I, s sigma I or u sigma I, u dagger sigma I u, এরকম একটা unitary transformation দিয়ে দাও, that also will be a valid solution. S can be any unitary matrix. So infinite number of them, but you choose one convenient one, and this is sometimes dictated by the very physics application that you have in mind. We'll have, because in my group theory class I have introduced one representation which is called chiral representation, if you remember. It comes very naturally when you consider boost, one on the left side and on the right side, and connect them, you get left chiral and right chiral, and then you combine them, you get a reducible representation, and then you say that if I want to invoke parity also, then it will furnish an irreducible representation, and then you get combine left chiral and right chiral, you get 4-component Dirac spinner. But here the approach I am taking is different. It is a historical approach that Dirac took. Okay. But all of them are the same kind of thing. So does it answer your question? Huh? So these is the condition that gamma mu had to satisfy. And these condition, this anti-commutation relation is called Clifford algebra. Okay, Clifford algebra. So, in 2 or 3 dimension, we have already seen the solution of the Clifford algebra is given by the Pauli matrices. In 2 dimension, 2 of them, and 3 dimension, all 3 of them are necessary. Okay. So now I want to find what is the representation. So I give you the solution. You check for yourself. Huh? The solution is simple. So this is gamma 0 is 1 minus 1. Gamma I. This is the solution. These are 2 by 2 matrices. So the first block is a 2 by 2 identity matrix. Second diagonal block is minus of identity matrix. Elsewhere it is 0. Okay. Here also the first block, both the diagonal blocks are 0. Off diagonal blocks in one case is Pauli matrix. For the gamma 1 it will be sigma 1, gamma 2 it will be sigma 2, gamma 3 it will be sigma 3. And here it is minus of that. You can check that if you substitute it here component wise, you can fulfill this condition. This is a solution. This is standard one of the canonical choices called standard representation. Okay. Okay. Mukta khule. No. As I told you, even in 2 dimension, I have written you U sigma, I sigma. There are infinite number of choices. Infinite. But all the choices are related by this kind of so-called unitary transformations. And the choice you make when you apply in one particular problem is dictated by the physical situation you have, dictated by physics. Huh? Eta? Oh, you demand, but you choose another gammas satisfying these things. So you means you have gamma prime mu. Let me choose gamma s inverse. Actually, not only unitary, means any transformation of this form will do it. Let me check. So if they satisfy the Clifford algebra, I want to see under what are the condition on S, any similarity condition, similarity transformation will do, not only unitary. So you see gamma prime mu will be S gamma mu S inverse S gamma nu S inverse. Okay, then you just add this wise S gamma mu S inverse S gamma nu S inverse plus the opposite S gamma nu S inverse S gamma mu S inverse. Okay, you can write like this. S inverse S will cancel. Here also S inverse S will cancel. So what you will have S gamma mu gamma nu. Again here it will come in the opposite order. S inverse. Okay, and this you know is twice eta mu nu, twice eta mu nu identity. So S identity, S inverse, which is again identity, twice eta mu nu identity. So any similarity transformation will give you. So I was not completely correct earlier, thanks. Any similarity transformation will relate these things. So if one gamma satisfies these things, another gamma who is related by S gamma mu S inverse will also satisfy these things. So I have infinite number of choice. It should be non-singular transformation. Okay. So this is the standard choice. Standard representation. Okay, so you can, I can leave this as a homework for you to verify. You have to just matrix multiply and check that this algebra is indeed satisfied. Okay. Okay. So now the Dirac equation is, now let me come to the Dirac equation. Finally, the Dirac equation, not towards the Dirac equation. You see? Now, you see, the Pauli matrices, as I told you, is the building blocks. Means Pauli matrice will occur naturally. ওটা ইট দিয়ে তৈরি যেমন এগুলো হয় সবগুলো ইটের তৈরি। Pauli matrice গুলো হচ্ছে something like ইট, ওগুলো দিয়ে তৈরি, অনেকগুলো ইট লাগবে আর কি। Okay. So the Dirac equation is actually Dirac operator. Strictly speaking, I should put a plus or minus sign here to make it Hermitian. But I was not that careful here. But ideally, I should make it Hermitian now, since I am going to apply it to quantum mechanics. So Dirac equation, as it stands now, will be given by I gamma mu del mu minus m psi. This x is space-time point event. Okay, so this is the Dirac operator as I have defined. I is to make it Hermitian. Minus m represents mass. Okay. Sometimes a shorthand notation is used like this.
স্যার বলছি এইটা কি লিখলেন একবার বলবেন?
Huh?
এই যে ইকুয়েশনটা এখন লিখলেন psi x দিয়ে, এটা একবার বলবেন কি বললেন?
No, this is the Dirac equation I have just written down. I have multiplied by I the Dirac operator. Actually, this I should, the entire thing is Dirac operator, I should say, if I demand is to be Hermitian. And the Dirac, these are called Dirac spinor. Dirac spinor is an eigen spinor of the Dirac operator with mass as the eigenvalue. You follow? Mass is the eigenvalue. So Dirac operator admits eigen spinors. These are spinors. Why it is spinors? For a reason again I have explained. It transforms under SL2C and all that, but I will tell you again from this perspective why. because they are neither like scalars nor like vectors. Means they fall in between. I will have to find their explicit transformation property. So this is the Dirac equation. A common notation is used if you have gamma mu. These are called Dirac's gamma matrices. If you contract with some a mu is any 4 vector. I, in short, write it as a slash. This is the notation has been introduced by Feynman called a slash. Okay. So you can write it in both ways, all possible. Means I del slash minus m psi is equal to 0. Or if you identify I del as p, I del mu as p mu, then you write p slash minus m psi is equal to 0. Okay. So you can see the property that I will be using very frequently, that a slash square, calculate, you can see it will be gamma mu a mu, another a slash will come gamma nu a nu. These a's are ordinary four vectors. Each components are numbers, they are not matrices or anything. Okay. So these are symmetric under interchange of mu nu, and it has got no symmetry. So only the surviving part, as I told you, will be the symmetrized part. Okay. So symmetrized part will be half gamma nu a mu, and this is twice eta mu nu identity. 2 will cancel, so it will have eta mu nu a mu nu, which is a square. Full form is obviously, you know, a naught square minus a vector square. Right? A vector means 3 vector I am talking about. A1 square plus a2 square plus a3 square. It's okay? So you see, the moment you have a slash, you square it, that slash you can delete it in the ultimate expression. It becomes just a square. This is a trivial identity, but it's very useful. Okay? So now you can check. Total a square purotai. A square is a 4 scalar, Lorentz scalar quantity. Na? This is a Lorentz scalar. You go to another plane, a naught will change, a vector, 3 vector will change, but the difference between the squares will be preserved, will be remain invariant. Okay. So this is just an identity. So now you can check that these are all different forms of Dirac equation. You can check that if you apply by p slash plus m both sides, multiply both sides by p slash plus m, p slash minus m psi is equal to 0, then what do you get? This is like m is just a ordinary number, C number. So you can your high school identity a plus b into a minus b equal to a square minus b square, you can write. So it will become p slash square minus m square psi is equal to 0. Okay, and p square is what? P square is, p slash square is p square minus m square psi is equal to 0. And what is p square? As I told you, it is nothing but p naught square minus p vector square minus m square acting on psi is equal to 0. And this is nothing but Einstein's dispersion relation I have written earlier. P naught is the energy and p vector is. So it says the Dirac equation indeed is in conformity with Einstein's dispersion relation. It doesn't change that thing. It has to be respected. It is very sacrosanct. Okay. So Dirac equation indeed satisfies Einstein, and each component psi, since you see these gammas are 4 by 4 matrices. So these psi's have to be 4 component objects, and they are called Dirac spinors. Okay. So psi has to be 4 component spinors like psi 1, psi 2, psi 3, psi 4. So this shows that each of these components individually will satisfy these Einstein's energy momentum conditions. This is E square and this is minus this. This is just a P square plus M square. Okay. So E square equal to P square plus M square. This is the Einstein's energy momentum condition. So it is indeed satisfied by all the components individually. And the 4 component object. So unlike your Klein-Gordon case, where it was involved only a scalar function, 1 component object, here you have a 4 component object. But it is not a 4 vector. A transformation property is completely different from a 4 vector. That I will need to find out. Okay. So this is called Dirac spinor. Okay. And I need to find out its this thing. So now let me see what are the probability currents and see whether probability can have a well-defined interpretation in this case. I expect to see a well-defined interpretation to emerge because now time derivatives also occurs linearly, first order time derivative. With this hope, let me try to do it. So let me start from here. So I can write this thing as this thing. I can take, remember Schrodinger equation, how do you find the probability current? You take Schrodinger equation, takes its complex conjugation, right? And then multiply by the other thing. If you take if you get psi star, then you multiply by psi. For the psi, you multiply by psi star, take that difference, and from there. So same technique will be adopted here. But unlike there, it involves the 4 component Dirac spinors. So here complex conjugation will not be useful. It will be the rather Hermitian conjugation. Okay. So let me take Hermitian conjugation of both sides. So what will happen? Psi dagger will come here. The moment you take Hermitian conjugation, order will be reversed. Complex conjugation case, order reversion was not there. Okay. And then you have minus I gamma mu dagger, del mu. But you see, del mu here was acting on psi from the left. Okay. But here it will act from the right because psi has gone here. So del mu has to act from the right. So I have to put an arrow mark indicating where from it is acting. Okay, minus m is 0. Okay. Now you see the representation I have written down, I just erased. You can check that gamma 0 it satisfies is Hermitian. Gamma 0 dagger was gamma 0 because it is block diagonal, the identity minus identity. So it is Hermitian. On the other hand, gamma i's were sigma I minus sigma I along the off diagonal. So if you take Hermitian position, minus sigma will come there and plus sigma will come there, so it will become a minus sign. So you will have gamma I dagger equal to minus gamma I. Okay. There is so you may be feeling bit uncomfortable that we have treating space and time components separately, segregated manner. But don't worry, I can write down it in a more covariant form in this way. Gamma mu dagger is equal to gamma 0, gamma mu, gamma 0. You put gamma mu equal to 0, the gamma 0 put mu equal to 0. So gamma 0 dagger is equal to gamma 0, gamma 0, gamma 0. Gamma 0 square is identity. It has to be, because Clifford algebra says you gamma mu, gamma nu is equal to twice eta mu nu. So gamma 0 plus gamma 0 again. If you put mu nu both 0, so gamma 0 will be twice eta 0 0. Types identity matrix is there, which I am not writing. I hope you understand it. Okay. So this will be gamma 0 square plus again opposite order again gamma 0 square. So 2 gamma 0 square is equal to 2, eta 0 0 is 1, so it is 2. So gamma 0 square is identity. So the gamma 0 square is equal to 1. If you do it gamma 1, for example, gamma 1, then you will get 1, 1, which will give you minus 2. Right? So we'll get gamma 1 square will be minus 2. So gamma 1 square will be minus 1. For any special thing, so likewise 2, 3, gamma I square will be minus gamma I. Okay. And gamma 0, the moment it is distinct, gamma 0, gamma I, or gamma 1, gamma 2, their anti-commutator will be 0 because this is diagonal. Okay. So it will be 0. So what will happen is that gamma 0 square identity, so you have, this is gamma 0. So gamma 0 dagger is gamma 0, you have recovered this thing. Okay. And then put mu is equal to identity, semi special index. So you have gamma I dagger is equal to gamma 0, gamma I, gamma 0. And gamma 0, gamma I is equal to, as I told you, is minus of gamma I, gamma 0. Right? As follows from here. You put mu equal to 0 and gamma nu is equal to I is equal to twice 0 I, which is 0. So gamma 0, gamma I, gamma 0, gamma I plus gamma I, gamma 0 is equal to 0. So gamma 0, gamma I is equal to minus of gamma I, gamma 0. The moment you interchange two different gammas, it will become a minus. So here you interchange, you get minus, gamma 0 goes there, gamma 0 square, gamma I, and gamma 0 square is identity, which I have just erased it here, so it will get minus gamma I. So gamma I dagger is equal to minus gamma I. So you can write in a compact form this relation. I hope it is clear to you. Hala? Clear? সবাই ক্লিয়ার তো? দেখো না বুঝলে বলো। কারণ আমি পরে শুনেছি অনেকে বলেছে গ্রুপ থিওরি ক্লাস বোঝোনি তোমরা অফলাইনে। আমি তো অবাক হয়ে গেছি, আমাকে তখন কেউ কিছু বলেনি। হ্যাঁ, মানে অনলাইনে অসুবিধা আমারও হচ্ছিল, বোর্ডে যেরকম সচ্ছলতা আছে পড়ার সেটা নেই। আর আমি এখন রিসেন্টলি পেন ট্যাব কিনেছি সৌমিতের অ্যাডভাইস নিয়ে, এখনো ভালো রকম করিনি, খুব বাধ্য হলে করবো, এই জন্য আমি এসে করাচ্ছি। আমাকে বাড়ি থেকে কোভিড বাড়ছে বলছিল গিয়ে পড়িও না, বাড়ি থেকে পড়া, আমি সুবিধা পাই না আমি। হ্যাঁ, কিন্তু একটু দৌড়ে আসার পরে তোমরা না বুঝে মাথা নাড়ো, তাহলে কিন্তু তোমরা আমাকে মিসগাইড করছো, মনে রাখবে, ইউ আর মিসগাইডিং মি। বুঝতে পারলে তো? তো দায়িত্ব তোমাদের উপরে বলার যে বুঝতে পারছি না, প্রশ্ন করবে এই করবে। তো যাই হোক, তো এটা ক্লিয়ার তো দিস? হ্যাঁ, তো আমি I can replace this gamma mu dagger by this thing here. So I can write psi dagger minus I gamma 0 gamma mu gamma
স্যার
0. হ্যাঁ
স্যার বলছি রাইট, মানে ডান দিকে যেগুলো লিখেছেন আরেকবার একটু পড়ে দেবেন।
বুঝতে পারলাম না।
মানে যে কমিউটেশন রিলেশন গুলো লিখেছেন অ্যান্টি কমিউটেটর দিয়ে, হ্যাঁ 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 হ্যাঁ, ওইগুলো একটু পড়ে দেবেন একবার।
এইটা
হ্যাঁ হ্যাঁ স্যার, ওখান থেকে একটু লাস্ট অব্দি।
আচ্ছা, তো না এটা বলছে, এটা তো আমার ক্লিফোর্ড অ্যালজেব্রা অরিজিনাল শুরু করেছিলাম, তাই না?
হ্যাঁ স্যার, হ্যাঁ ওটা বুঝতে পেরেছি।
এখন তুমি যদি এখানে যদি দুটো ডিস্টিংক্ট বসাও, মিউ ইকুয়াল টু 0, নিউ ইকুয়াল টু আই, তাহলে কি হবে? ইকুয়াল টু আই তাহলে হবে 2 ইটা 0 আই which is 0। তার মানে বোঝাচ্ছে গামা 0 গামা আই প্লাস গামা আই গামা 0 বাই ভেরি ডেফিনেশন অফ অ্যান্টি কমিউটেটর ইজ 0। তার মানে গামা 0 আর গামা এর মধ্যে যখনই ইন্টারচেঞ্জ করবে তখনই মাইনাস সাইন পিক আপ করবে। ওকে, the moment you interchange gamma 0 and gamma I, they will pick up minus sign. In fact, any gamma mu whenever mu is not equal to nu, when you interchange gamma mu and gamma nu, if mu and nu are not equal, then itself it will pick up a minus sign. এটা নাম্বার ওয়ান। দ্বিতীয়ত তুমি ক্লিফোর্ড অ্যালজেব্রা লাগিয়ে দেখো, তুমি যদি দুটো সমান হয়, তো গামা 0 স্কোয়ারের জায়গায় ইউ উইল গেট 1, আর গামা 1 স্কোয়ারের জায়গায় ইউ গেট -1। যে মাইনাস সাইনটা একটু কি হয়ে গেছে, পরিষ্কার করে -1। 2 gamma 1 square is equal to -2, so gamma 1 square equal to -2. It is likewise gamma 2 square also -1, gamma 3 square also -1. তো ঠিক আছে, তো এখন আমি এটাকে লাগিয়ে আমি এটা প্রমাণ করলাম, gamma mu dagger equal to gamma 0 gamma mu gamma 0. So I substitute it here and I have del mu minus m is equal to 0. Okay, so now let me do this thing. I define a quantity which is psi dagger. Psi dagger, you see, psi was a column matrix. Psi dagger will be row matrix. Dagger has Hermitian conjugate multiplied by gamma naught, which is a 4 by 4 matrix. So it will be another row matrix. So I denote it, I define psi dagger gamma naught by definition is psi bar. Okay, I define it like this, psi bar. This is a খুব standard convention. Okay, আমি এটা মুছে দিতে পারি। হ্যাঁ, কি? না না না, দু লাইনে হয়ে যাচ্ছে। আমি কেন বোর্ড হয়ে গেছো? হ্যাঁ, আচ্ছা, না আমি ছেড়ে দেবো, এটা করেই ছেড়ে দিচ্ছি। হ্যাঁ
হ্যাঁ স্যার,
হ্যাঁ
হ্যালো।
বলো।
হ্যাঁ স্যার, বলছি যে ওই লাস্টে ওটা কি লিখলেন, ডি ইকুয়াল টু ইন্টিগ্রেশন দিয়ে?
কোনটা?
ওই ডিরাক
or define psi dagger gamma naught, এটাকে psi বার বলছি।
হ্যাঁ না, তার আগে ওটা কি লিখেছেন? ও ডিফাইন, আচ্ছা আচ্ছা, সরি সরি।
ফাইন, হ্যাঁ
ও আচ্ছা।
ওকে, ঠিক আছে। তো আমি এখন কি করব, এই দিক দিয়ে একটা psi দিয়ে মাল্টিপ্লাই করব, এই দিক দিয়ে অ্যারোটা এই দিক দিয়ে আছে, ঠিক আছে। আর বাঁ দিক দিয়ে psi বার দিয়ে মাল্টিপ্লাই করব। আর এটা যদি, এটা আমি আরেকটা স্টেপ লিখছি, এটা থেকে আমি পাচ্ছি মাইনাস আই psi বার, গামা নটটাকে নিয়ে চলে এলাম, হ্যাঁ দাঁড়াও, psi বার আই গামা মিউ গামা নট ডেল মিউ হ্যাঁ মানে এটাকে আমি করছি কি, আমি psi ড্যাগার গামা নট, এটাকে আমি psi মানে গামা নটটাকে বাইরে বের করে দিচ্ছি। আর এখানে আমি ডান দিক থেকে আরেকটা গামা নট দিয়ে মাল্টিপ্লাই করছি, ঠিক আছে। তাইলে দেখো এখানে কি পড়ে থাকবে, মাইনাস এম গামা নট, আর এই গামা নটটা থাকবে না, গামা নট স্কোয়ার 1 হয়ে যাবে, মাইনাস এম গামা নট থাকবে, ঠিক আছে। আর এটা হলো এইটা, হ্যাঁ ধরো, হ্যাঁ দিস ইজ ইকুয়াল টু 0, ওকে। আর রইল এইটা, তোমার রইল এন হাইডেগার আই বার মাল্টিপ্লাই করলাম, গামা নট হ্যাঁ কোথাও একটা, না আমি আমার এটা ছিল psi ড্যাগার, আমি এটা ওইটাতে এটা বসালাম, তারপর ডেল মিউ, আর একটা গামা নট দিয়ে রাইট থেকে মাল্টিপ্লাই করলাম, হ্যাঁ একটা বাইরে গেছে, বাইরে গিয়ে এটাকে psi ড্যাগার বানালো। আচ্ছা হ্যাঁ, তো এই গামা নটটা বাইরে চলে যাবে, মানে আমি এই গামা নটটাকে এখানে নিয়ে যাচ্ছি, তো এখানে গামা নট থাকবে না, এই তো, রাইট, আই ওয়াজ মেকিং মিস্টেক। Okay, so now I am subtracting এটা এই ইকুয়েশন নাম্বার 1 আর এই ইকুয়েশন নাম্বার 2, এইটা থেকে এটা সাবট্রাক্ট করছি, তাহলে কি দাঁড়ালো দেখো, সাবট্রাক্ট করলে মাইনাস এম psi বার না এই সরি psi ড্যাগার, এটা হলো, তারপরে এটাকে আবার ডান দিক দিয়ে আরেকটা psi দিয়ে মাল্টিপ্লাই করে, মানে psi এর উপরে লাগাচ্ছি নাকি, মানে হ্যাঁ মানে ওই জিনিসটাকে আমি psi দিয়ে মাল্টিপ্লাই করার আগে আমি গামা নট একটা মাঝখানে ঢোকালাম, ওকে, বাট লেট মি ডু ইট, আমি একটু কনফিউশন হয়ে গেছি, দাঁড়াও জাস্ট লেট মি ডু ইট अगेन ফ্রেশ। psi dagger minus I gamma 0 gamma mu gamma 0 minus m gamma 0 square এখানে 1 আছে এটা gamma 0 square করে দিলাম is equal to 1 ঠিক আছে হ্যাঁ তারপরে আমি এই গামা নট আর এই গামা নট কমন নিলাম এটা হয়ে গেল psi বার minus I gamma mu gamma naught minus m gamma naught is equal to 0 ঠিক আছে ওকে I have taken gamma naught common এখান থেকে একটা গামা নট নিলাম এখান থেকে এই গামা নটটা নিলাম দিস বোথ গামা নটস psi dagger gamma naught psi bar হয়ে গেল as per my definition so minus I gamma mu gamma naught আর আরেকটা গামা নট এখানে থাকলো হ্যাঁ del mu sorry del mu okay I have just এখানে 1 আছে ওখানে গামা নট স্কয়ার বসালাম ওকে then I have taken gamma naught common মানে এখান থেকে গামা নট কমন নিলাম নিয়ে psi dagger gamma naught psi bar হয়ে গেল ওকে psi bar is psi dagger gamma naught okay what I'm left with minus I gamma mu del naught del mu left arrow minus m একটা গামা নট পড়ে থাকলো ওকে তো এখন আমি গামা নট ডান দিক দিয়ে মাল্টিপ্লাই করি হ্যাঁ এইটাতে হ্যাঁ ডান দিক দিয়ে এটা তো বাঁ দিক দিয়ে আছে না this del mu acting from right gamma the psi dagger is a row matrix now psi original psi was a column matrix psi will be row matrix না psi টা যদি এরকম হয় psi 1 psi 2 psi 3 psi 4 তাহলে psi dagger will be psi 1 star psi 2 star psi 3 star psi 4 star ঠিক আছে it will be column matrix then it will multiply with this gamma naught row matrix time gamma naught is a 4 by 4 matrix multiplication is well defined it's okay okay so now I multiply again by right by gamma naught multiply by gamma naught so this gamma naught disappears gamma naught square is 1 again this gamma naught square is 1 because gamma naught can pass through del mu this is a numerical matrix and del mu acts on functions you don't have to so they commute they act on different places okay so then you have psi bar minus I gamma mu del mu minus m is equal to 0 okay then again I multiply the whole this is a zero operator so to say so acting on psi it will be 0 if you have a zero operator acting on any psi it will be 0 and I have these things so what I do I subtract 2 from 1 so 1 minus 2 gives me what psi bar I gamma mu del mu plus del mu psi is equal to 0. The mass term cancels. যদি বাদ দেই যদি psi bar minus m psi bar psi, এখানেও minus m psi bar psi, that will cancel. Because subtracting 1 minus 2. So what we'll have is that I gamma mu psi bar del mu right arrow psi, and it will be plus I gamma mu and psi bar del mu acting from the left. You can forget about the I because it is 0, it's a constant, so you can forget about the I. So what we will have is, you can write down del mu psi bar, del mu acting on psi bar, gamma mu psi. This gives you the first term, and the second term will give you psi bar gamma mu del mu psi is equal to 0. Okay. Okay, psi bar del mu psi. So that's how it. Is it okay? So now you can write down these as del mu psi bar gamma mu psi. This is equal to 0. So okay, Kala. ঠিক আছে Shomit? I is a factor, I just cancelled it. So del mu psi bar gamma mu psi. The second term plus psi bar gamma mu del mu psi. So I can take del mu to Leibniz room, this thing. So identify this is nothing but my forecurrent J mu. So identify my forecurrent is this thing. Okay. So now you ask the question, is the forecurrent, so this is the continuity equation, del mu J mu equal to 0. Right? And from the continuity equation you read off what is the probability density. Time component gives you the probability. So the J0 gives you the probability density. It should give you, if the interpretation is possible, psi bar gamma 0 psi. But psi bar, as I have defined, is psi dagger gamma 0. Then again another gamma 0 psi. Gamma 0 squared is 1. So psi dagger psi. So if your psi dagger is a row matrix, psi is a column matrix, psi dagger is a row matrix, you will get psi 1, psi 2, psi 3, psi 4. You will get psi 1 mod square plus psi 2 mod square plus psi 3 mod square plus psi 4 mod square. So all positive. So J0 is indeed positive, as Dirac anticipated. So the moment he made all the spatio-temporal derivatives linear, he achieved a big success. He could identify the probability current with the time component gives the probability density, because it is probability positive definiteness is ensured. Okay, he could identify that as the probability density. Okay, so J0 is psi dagger psi is positive definite, and therefore can be interpreted as probability. Okay, let me finish it here. Okay. Any question at this stage? Huh? I take the number. এখানে তো কোনো তোমার যদি ধরো I times something, some number gives you 0, so that number has to be 0. I তো just a number. ঠিক আছে, সব স্টেপ, কোনো কোশ্চেন নেই তো? হ্যাঁ, কোনটা কোনটা ডেল মিউ ড্যাগার? তুমি এখানটা আসো, কোনটা বলছো আমি বুঝতে পারছি না। না ড্যাগার না, এটা জাস্ট কেটে দিয়েছি। না না না, ডেল মিউ লেফট অ্যারো,
ওটা প্লাস।
না প্লাস, ডেল মিউ লেফট অ্যারো, এটা directing from right arrow. Psi dagger gamma I is a defined quantity, but is not very useful. Psi dagger gamma 0 is psi bar, that will come again and again. This is a useful thing. And multiplication is well defined. Psi dagger gamma mu for all mu's is well defined. Now it is a row matrix, na? 1 into 4 times 4 by 4. Row column match only to well defined. J I psi dagger gamma I psi. তখন আসবে মানে psi dagger psi bar gamma I psi. তো তখন হবে তোমার psi dagger gamma 0 gamma I psi. তোমার JI will be psi bar gamma J mu was what? I have written down. Psi bar gamma mu psi. So it is JI psi. So this will be psi dagger gamma 0 gamma I psi. Okay. Okay. So everything is well defined. Shamit, any question? No বক্তব্য? হ্যাঁ হ্যাঁ, এটা ফার্মিওনিক, কিন্তু আমি এখনো ডিক্লেয়ার করিনি। হ্যাঁ, চুপিসারে ঢুকেছে, ওকে এখন চিহ্নিত করতে হবে, এই জন্য অনেক স্টেপ নিতে হবে, আরো অনেক দূর যেতে। হ্যাঁ, ইনফ্যাক্ট এটা ফার্মিওনিক খালি না, মানে এগুলো দাঁড়িয়ে যাবে কোনো নাম্বার সিস্টেম দিয়ে একে রিপ্রেজেন্টই করা যায় না, এগুলোকে বলে গ্রাসম্যান ভেরিয়েবলস। হ্যাঁ, এগুলো পরে ফিল্ড থিওরি দিকে আসবে, পরে আবার আমরা কোয়ান্টাম মেকানিক্সে ব্যাক করবো। আমরা যদিও দেখছি আমরা এখানে কোয়ান্টাম মেকানিক্যাল ইন্টারপ্রিটেশন সাকসেসফুল, প্রবাবিলিটি ইন্টারপ্রিটেশন গোস থ্রু, I can proceed with the quantum mechanics. Okay, the quantum mechanics proceed করলে later I will show that there is some still paradoxical situations. বোঝা যায় যে one particle description of relativistic quantum mechanics is an incomplete theory. You are essentially, which essentially forces you to invoke quantum field theory. When one particle relativistic quantum mechanics is incomplete and inconsistent theory. সেটা পরে বলবো। ক্লেন গর্ডনে যেমন প্রথম ধাক্কাতেই ফেল করে গেছিল, এখানে প্রথম ধাক্কা পাস করে গেছে, কিন্তু পরে কয়েকটা ধাপে গিয়ে আটকে যাবে। হ্যাঁ, এটা আমরা আলোচনা করবো। এই জন্য কোয়ান্টাম ফিল্ড থিওরি becomes an inevitable formalism if you consider a merger of relativity, special relativity and quantum mechanics. বুঝতে পারছো? That is the quantum field theory. But a single particle interpretation is not enough. Single by any fixed number of particles, n number of particles. Quantum mechanics you can do for n number of particles. Is not enough. Non-relativistic quantum field theory you can, quantum mechanics you can do for n particle system. But non-relativistic situation are, there is no particle creation or destruction. একটা particle create করতে mc square energy লাগে. Non-relativistic limit is c tends to infinity. Infinite amount of energy লাগবে। On relativity theory, if you come to non-relativistic theory, you have to take c tends to infinity limit, effectively. Speed of light is instantaneous. তুমি ওখান থেকে আসো, তাহলে you take, so for a particle, the rest mass becomes infinite. You do not have so much of energy. In non-relativistic limit, world of course doesn't respect your this thing, whether you have this kind of thing. So there is no possibility of creation or destruction of particles. But relativistic theory, you have a possibility of creation and destruction of particles. একটা পাই নট একটা মেসন ডিসইন্টিগ্রেট করে দুটো ফটন দিয়ে দিচ্ছে, আগে ফটন ছিলই না, আগে খালি একটা পাই নট পার্টিকেল ছিল মেসন, ওটা তারা ডিসইন্টিগ্রেট করে দুটো ফটন দিচ্ছে। তো পাই নটের কি হলো? নন রিলেটিভিস্টিক কোয়ান্টাম মেকানিক্স ইউ ক্যানট ডেসক্রাইব ইট, a particle disappearing where wave function psi of x, you are describing the evolution, the particle disappearance তোমার ফর্মালিজমে কোথায় আছে? The particle creation কোথায় আছে? Not there. So in order to describe such a situation, যেটা এলএসসি তে যে এক্সপেরিমেন্ট হিগস বোসন টোসন বের করেছে, ওটা অনবরত পার্টিকেল ক্রিয়েশন ডিস্ট্রাকশন চলছে। So quantum mechanics is not enough there. Quantum field theory is a basic thing. It is a বলতে পারো মডার্ন ফিজিক্সের মোস্ট ইম্পর্টেন্ট অ্যাসপেক্ট কোয়ান্টাম ফিল্ড থিওরি। সায়ন তোমাদের দেখিয়েছে যে স্ট্যাটিস্টিক্যাল মেকানিক্সও তার ইম্প্যাক্ট কি নন রিলেটিভিস্টিক সিচুয়েশনে। আশা করি বুঝতে পারছো কোয়ান্টাম ফিল্ড থিওরি মানে সমগ্র, এবং কি কন্ডেন্স ম্যাটার ফিজিক্সেও তার অ্যাপ্লিকেশন। আনফর্চুনেটলি ইন্ডিয়াতে কন্ডেন্স ম্যাটার সেরকম করা হয় না, মানে সবাই খালি সিমুলেশন আর ওসবই করে, কিন্তু মেইন যে ফিল্ড থিওরিটিক্যাল অ্যাসপেক্ট অফ কন্ডেন্স ম্যাটারের খুব একটা করা হয় না। Field theory is a very difficult subject but most important. বিভিন্ন জায়গায় ফিল্ড থিওরি না শিখে এমএসসি ডিগ্রি পেয়ে যাচ্ছে। মানে তুমি বাংলা সাহিত্যে কেউ যদি বলে আমি রবীন্দ্রনাথ না পড়েই বাংলা সাহিত্য পাস এমএ করে নিচ্ছি, এটা হবে? এরকম আর শেক্সপিয়ার না পড়ে ইংলিশে এমএ করে নিচ্ছি জিনিসটা। ওকে, এটা একটু কালা এটা খুলে দাও তো কি মানে। Okay, onliners, I hope this is okay with you.
Yes, sir.
Okay, okay. I call it a day. I hope you don't have any further questions. If you have, we'll discuss it next time because they are going for refreshment.